Today we're going to talk about modulations, so the process we've been mentioning so far, which is perhaps the most important technological feature which allows us to actually emit and receive with antennas and to use the spectrum and utilize it properly. So first we're going to very briefly go about what modulation is and give the basic concepts with a very simple modulation using only sine waves, and then we're going to look at the general description of modulation for an analog signal and go into the more important for us, digital signal modulation. So first of all, so far we've seen that we have antennas, we've seen that we have signals, we've seen that signals generally require many different frequencies to be formed. They have a spectrum, and each signal in time is uniquely determined by its spectrum. So how can we actually form a signal if we need many different frequencies? And we have seen so far that antennas generally are used for a very small part of the spectrum, very tight part of the spectrum. So they're useful for some small range of frequencies, which are their working frequencies in which they emit or receive, but those frequencies are generally not the same as the frequencies that form signals. So just as a basic example, suppose we have a radio amateur antenna, so like a UHF antenna, which is roughly emitting at 430 megahertz. And suppose we want to emit a signal, and just very simple sine wave, no information at all, but suppose we want this sine wave to be at a lower frequency, say 100 megahertz. So we are emitting a signal which is 4 times lower in frequency than the frequency of emission of our antenna, and we can't just, feed it to the antenna, because we have already seen that somehow the physical characteristics of the antenna are reflected in the frequency that we emit. So we cannot simply feed this lower frequency, which means larger wavelength signal. So 4 times smaller frequency means 4 times larger wavelength, so the antenna will not be able to use this signal. So what can we do? Well, one very simple idea is to try to emit with the higher frequency signal, so with the 435 megahertz, but to encode within it the characteristics of the lower frequency signal. So somehow, we have 2 sine waves. We have what we call the carrier signal, so the signal which our antenna uses and which it uses to emit, which is at 435 megahertz in this example. And we also have our baseband or modulation signal, which is about 100 megahertz. So how can we embed the first in the latter? Well, the answer is that we have to modify one of the characteristics of the carrier in such a way as to actually understand what is the change of the baseband. And we know what the characteristic of a sine wave are. We already went through sine waves quite a while back, but I'm going to remind you quickly that a sine wave is uniquely characterized by its amplitude, by its frequency, and by its phase. So if we know these 3 numbers, we have completely characterized it, and these are the only 3 differences which we can have between sine waves. Well, in the case of electromagnetic waves, we also have polarization, so we can also distinct 2 electromagnetic waves by their polarization state. But just neglecting polarization at this point, we have these 3 capabilities. So we have these 3 characteristics which we can modify and in which we can embed the information of the lower frequency signal. So suppose we choose the amplitude. Of course, we can change the amplitude of our carrier signal, of our 435 megahertz signal, in such a way as to reflect the amplitude of the baseband or the lower frequency signal. And you can see this process, and you can see in this plot here showing, you have the combination of the 2. So you see that by combining them, by including the amplitude of the carrier signal to be the baseband signal, we actually get a secondary, you can say, change in the sine wave in such a way that the frequency remains the same at all times, but the amplitude changes, and the higher the amplitude of the carrier, the higher, respectively, is the amplitude of the baseband at that point. So you see, if we plot the baseband signal alongside the final formed signal, you can see immediately that we have the baseband as an enveloping signal, and by measuring at the other end this combination of carrier plus baseband, we can again extract information about the baseband itself. So you see, in this process we essentially embed the information of a lower frequency signal within the amplitude of a higher frequency signal. And we can use this higher frequency signal with our 435 megahertz antenna and still emit a much lower frequency. Maybe even not 100 megahertz, but maybe even kilohertz, so much lower. We spoke earlier that in general, our signals will require kilohertz, maybe even lower. So we should make sure that we are able to transmit these low frequencies in some way through the higher ones. Okay, but this was just the first possibility. So we can actually embed the signal within the amplitude. There is, however, one downside to this type of modulation. It's called amplitude modulation, obviously because we are modulating the amplitude. We are changing the amplitude and embedding the secondary signal within it. But there is one downside, and this is the fact that it's very prone to changes, to noises due to external interference. So what would happen if we had a lot of noise, if we had a lot of external signals being fed to the antenna as well? They would interfere and they would change the amplitude of this signal. So we would get a much distorted version of this final signal which we have here, and perhaps clearing it out would be pretty hard. Now there is another type of modulation which is known as frequency. So in this case we're going to manipulate the second characteristic of a wave. So we have FM, or frequency modulation, and essentially the idea is the same. So we have a central frequency in which our antenna works, and we have two small deviations from it. So we have this delta omega. It's a small deviation of frequency in such a way that it is modified, the frequency itself is modified to be a bit larger or a bit lower depending on the baseband signal. So you have in the formula, you see that we have the central frequency, the carrier frequency, plus this delta omega times the sine. So whenever the sine function of the baseband signal is highest, whenever we have the maximum of the sine wave, we have a bit higher frequency, and whenever the sine is lowest, so whenever it gives us -1, we have a bit lower frequency, and in between we have a whole range of frequencies. And the final result, again on the three plots, you see the carrier, the baseband signal, and the final modulated signal. And on the final result you can see that the frequencies are a bit different. So you can see wherever the sine wave has its maximum or minimum, the frequency is actually, they look a bit higher, and in the middle they seem a bit lower. So it's a bit harder to see it on this plot than with the amplitude modulation. It's a bit harder to see it, but this is actually a more secure way of encoding, of modulating in terms of noises, because you can easily modify the amplitude of a signal. If you have external interference, the amplitude undergoes a lot of modifications, but the frequency, you cannot change the frequency of a wave by interference. So even if your wave, if its amplitude changes a lot due to external noise, the frequency, in a sense, is more secure in terms of noises. So it's much safer to encode in frequency if you want to reduce the noise. So the last type of modulation we can consider, we have the last parameter which we saw, is the phase modulation. So again, it's the same idea. This time the frequency is a constant, this time the amplitude is a constant. We have the carrier amplitude and carrier frequency, but we add a small delta phi, so or maybe a large delta phi, which is a change in the phase, which depends again on the baseband signal. So whenever the sine function of the baseband is maximum, in this case we are showing a delta phi equal to pi to 180 degrees, so it's not very small, it's a flip by 180 degrees. So whenever we have the maximum of the sine wave of the baseband signal, you can see that this phase jumps by pi. And whenever we have the minimum, so whenever we have the sine of the baseband equal to -1, this phase jumps by -180, so minus pi. And you can see the result, it looks quite similar to the FM modulation. And you can see these clumps where we have the lowest and the highest points of the baseband signal. You can see respectively the change of the phase and how the sine waves, they seem to have different frequencies. Okay, but in general, we do not want to transmit sine functions. It's pointless. Okay, so if you transmit a sine function, you have no information. A simple sine wave, it has no zeros and ones. It's just the same all the time. So we don't want to transmit sine waves. We want to transmit actual signals which carry information. And how do we do this? Well, of course, we can decompose a signal in sine waves. We've already seen this before. A lot of what we've done previously was exactly Fourier transformations, and we can do something similar. In fact, if we take a finite spectrum if we again represent a signal as a pseudo periodic signal, so even if it's not really periodic, we just take a finite part of its band, of its bandwidth, we can compose it again as a sum of sines and cosines, so depending on the phase. So again, we can use the same technique of modulation by modulating our signal to encode each of these sine functions. And of course, we can generally make amplitude, frequency, or phase modulation for non-sine signals, so for a general function. And you can see an example of a Gaussian impulse, so a Gaussian function, which is very famous. We can use it, and again, we can encode such a signal which has a Gaussian shape, which can be up to a first approximation, it could be a 1 or a 0, doesn't matter. The point is that we can actually embed this again in the same way by using it as a baseband signal and using some carrier frequency and combining them in exactly in the same way. And the result of this modulation is that we actually get a sine wave which has the characteristic of its amplitude follows the Gaussian. And if we had done the same with the frequency, we would have had again a sine wave, the frequency of which changes based on this Gaussian only in a small range. So what about bandwidth? Okay, we have modulation, and we know that each signal, however, depending on how complex it is, depending on what its frequency domain is, it has different frequency components, so it has different bandwidth, it takes a different part of the spectrum. So if we want to embed this signal in a higher frequency signal, how much of the spectrum, what portion of the spectrum do we need? We learned before that a very important result, that actually the same bandwidth can be used to transmit the same amount of information. So if you want to transmit a phone call and you need 8 kilohertz, for example, it doesn't matter where you're going to put this 8 kilohertz. Is it going to be in the megahertz range or in the gigahertz range? As long as you have a bandwidth of 8 kilohertz, you can always do it. You can always transmit voice, let's say. So what is the case for these modulations, and how do we know what bandwidth we need? Well, it's, again, essentially it's the same idea. Depending on our baseband signal and its highest frequency component, we can immediately tell what is the required bandwidth for amplitude, frequency, and phase modulation. And to get the right reconstruction of the signal, it can be proven that for amplitude modulation, the bandwidth is absolutely independent of the actual amplitude. So in all cases with amplitude modulation, we need exactly twice the maximum frequency of the baseband signal. So if we have a baseband signal with highest frequency component, say 100 Hertz, then the bandwidth we need is going to be 200 Hertz, whatever we place it, if we're modulating by amplitude modulation. Now, for frequency and phase modulation, the bandwidth depends also on the small deviation. So we saw that with the frequency, we had a delta omega, or delta frequency, delta F if you like, which told us how much our frequency changes, the maximum and the minimum range within the central frequency. And in the same way, for the phase modulation, we had a delta phi, a change in the phase. So for the FM, we actually have twice the maximum frequency of the baseband signal plus this delta ni, so plus this delta of the frequency which we use to encode the information. And for the phase modulation, we have twice the modulating highest frequency, twice of the baseband highest frequency, times 1 plus the delta of the phase. So this delta phi which we use to actually change the phase to a bit higher or lower depending on our signal. So you see that in these cases, in the FM and PM modulations, our total bandwidth does not depend only on the signal we are transmitting, but also on the characteristics of our modulation. So the larger our frequency deviation or phase deviation is, the larger the bandwidth is, but this is a small price to pay compared to the noise resistance which we get for these cases.